We are fortunate today to have Doug Nordstrom, who is our current product manager for hose products with Swagelok in Cleveland. He has 25 years experience with Swagelok in a variety of Swagelok product and market categories, and a trained and educated graduate of Case Western University in mechanical engineering, and also an MBA from Kent State University. So thank you for joining us, Doug, and I'll go ahead and have you take it away.
Hey, thank you, Jen. And it probably is a wonderful morning where all of you are here in Cleveland. It's about 45 degrees and rainy, so pretty typical autumn day for us here. And thank you, everyone, for joining. We have a two-part hose selection and troubleshooting training class. We're doing part one today, of course, where we're going to talk about various hose types and proper selection. We start off relatively simple, and then we're going to talk about what kinking is in a hose and how to properly route a hose. The next part, a few weeks in the future, will be a little more detailed, more technical. We talk about the difference between conductivity and static dissipation, and we're going to talk about some different construction methods for creating hoses. One with softer materials on permeation and one on harder materials, metal core hoses, and how those are made and how they perform different in different applications. So again, today we're going to cover the part one topics, and it starts off relatively simple, but we do get a bit technical. So just to start off with, why does hose selection matter? It amazes me how often hose selection isn't really something that is thought of as being a very serious or important thing with a fluid system. Where in actuality, a hose is a very important product. It's the wear item of a fluid system, and it's usually one of the more common failure points. And these failures can be very serious. They lead to, of course, downtime, which can be very costly. It can waste product, and more importantly, it really can be very dangerous. An improperly selected hose can cause bodily harm or death, for that matter. And so really understanding the application and selecting the right hose for the job is a critical aspect that we take very seriously. We say failure is not an option, with taking into account all the application parameters when selecting the right hose for a job. The analogy I like to use, and I talk about this quite a bit as being the hose product manager, is no one will go out and buy a new car and not plan on doing routine maintenance, preventative maintenance to the tires. Everyone kind of understands that tires are a wear item, and they need to be rotated, they need to be pressurized, they need to be changed when they go bad. Otherwise, bad things can happen. And we get the question all the time is, how long will a hose last? Well, I say, well, how long will a tire last? It depends. Depends on what kind of roads they're being driven on, and you know how fast and how drastic of a driver you tend to be. Same thing with the hose. We can't really determine how long a hose will last, but what we have learned is that hoses last a very predictable amount of time in the same application. So it's always important to start that preventative maintenance program and start collecting data on how long a hose will last. And we can always help with determining how worn a hose looks, similar to a tire, to help you create that data to make sure that you have a safe environment for all the work associates around hoses. So with that said, we're going to jump into different hose types and understanding the proper hose selection with these types. And again, this starts off fairly simple, but what makes a hose and not a tube is that it's multi-layered. A lot of people seem to think that a hose means it has to be flexible. Well, that's not necessarily the case, because there's flexible tubing out there, and some hoses tend to be fairly rigid. They're not very flexible. So really what makes a hose is that it's multiple layered. And I break down the layers or the components into these four. Every hose has a core material. The picture shown here, it's a soft core material, which is PTFE or Teflon. And then the hose has a reinforcement. And many times this reinforcement is a braid. In this picture, you see the black braid is a fiber braid, and the grayer braid is a stainless steel braid. This hose has both. and we'll talk a little bit about that. But the braid gives the hose its pressure rating. A core material typically can only withstand 30, 40, 50 psi, where once it's braided, hoses can withstand thousands of psi depending on the braid material. The braid many times isn't covered. It doesn't have to have a cover, but many times it's covered to protect the hose, protect the user from maybe damaged braid wires, injuring an individual, or also making the hose more cleanable. The cover is very easy to wash down, so the outside of the hose can stay clean. And the cover can also provide some abrasion resistance to allow the hose to last longer if it's being dragged along the ground or rubbing up against something. So again, the cover needs to be taken into consideration. And then the end connection, of course. And every hose has two end connections, obviously. But these end connections are important in that the end connection needs to be the stronger point of the hose assembly. So when we look at an entire hose assembly, one end connection to the bulk hose to the other end connection, we make sure that the end connection to the hose connection is the strongest point. We never want a hose end connection to come off the end of the hose because that's a very dangerous failure method. It allows for gross leakage, first of all, and second of all, that full separation can create a whipping effect where the hose is now flying around in the air and can obviously be a very big safety concern. So we always want the actual bulk hose, when overpressurized, to be what bursts. It's a much safer failure mode. So what we say is we like to select a hose understanding the needs of the application from the inside out. That's what we're getting to here in this slide. So if we're looking at a cross section down the center of a hose, we always want to consider the core tube. What does the core tube need to withstand? What is the core tube media going to see? How much reinforcement is needed and what type? How much pressure is needed? What does the reinforcement need to be able to do? What temperatures is it going to see? What cover, if any, are needed? And then, of course, what end connections needed to be able to connect it to the system. So all these four need to be considered when selecting the right hose. We use an analogy. It's actually not something I can claim as my own. It's not a Swagelok analogy, but it's the acronym S.T.A.M.P.E.D. It's something that was developed by an industry group called NAHAD, and it's intending to go through all the different aspects of an application that need to be considered when selecting a hose, and they're listed here. So how big does a hose need to be, of course? What temperature is the hose going to see? First of all, media temperature or outside temperature, because that can come into play with what the core tube sees versus what a braid or cover is going to see as far as temperature goes. What kind of application is it? Is it dynamic? Is it static? How much is the hose going to be dragged around or moving? And then what media is it going to see? What does the core tube need to be chemically compatible with? What's the pressure going to be? What are the end connections? And then also, obviously what kind of delivery is needed? Is anything special needed for the delivery of the hose? But all these need to be considered when looking at those four layers I mentioned before, with the core tube, the braid or reinforcement layer, the cover, and the end connection. These are four main types of general industrial hoses that you'll see. They all act differently in different applications. So again, we see these misapplied very commonly, and it's important to understand the strengths and weaknesses of each kind. The top one is actually a metal core hose. So that internal core tube is a convoluted metal core that is convoluted in order to create the flexibility. If it was just a straight thin wall tube, of course it would kink and not be flexible very quickly. So the metal core is convoluted to give it some flexibility, and end connections are welded to that all metal hose. The second one down the list is a Teflon, fluoropolymer, PTFE, whatever you want to call it, core tube, which is reinforced, in this case with both fiber and stainless steel braid. The third one is a thermoplastic hose, really designed to take hydraulic impulse pressures, was the main purpose it was first developed. And then the last one is a rugged rubber, down and dirty type hose, very commonly used in the general industry markets, or for airlines, for example. Each one of these has its own performance characteristics based on those core tube materials. We're showing a little chart here showing some basic advantages and disadvantages. Metal, of course, being a wide temperature range. It also practically eliminates permeation, which we'll get into in the next section of this on the next day we do our tech talk. It's much better for vacuum applications, but it will, like a paper clip, bending a paper clip back and forth too many times, it'll break. Metal hose will break sooner than the rest of these. PTFE fluoropolymer is a good compromise where it has good chemical compatibility with most anything. It allows for cleanability because of the smooth bore. It does permeate some, and it runs into an issue with static dissipation, which again, that's a part 2 topic we'll get into. But you need to be careful when specifying a PTFE core hose with static dissipation. It can cause leaks very quickly. The nylon or thermoplastic, they're mainly designed again for hydraulic. They're very rugged. They take pressure impulses. And then rubber, very durable. You can run it over, you can stand on it, and it most of the time is going to last for a very long time. But again, these softer materials won't have the same temperature and pressure ranges as the harder metal materials. This is intended to be a cheat sheet showing advantages and disadvantages of the types. And again, this is something where we see the wrong hose in the wrong application very often. And it's not an indicator that it's a poor quality hose, but if we take a metal core hose and put it in a impulse application where pressure spikes are happening very commonly, the metal can't absorb those pressure impulses like a PTFE Teflon core or a thermoplastic core hose. So even though that could be a very high quality and high priced metal core hose, it won't last very long. And so it's just the wrong hose in that application. So it's important to really look at all these different characteristics when selecting the right type of hose. And then of course there's multiple hoses in each type. So selecting the right hose can be a difficult thing to do, but it can really extend the life of a hose in an application by 10-fold, 100-fold of what the wrong hose would do. The same applies when looking at braid material. So far I was just talking about really core tube. Braid material, there's a lot of engineering that goes into a braid of a hose. I wouldn't have thought it before my time working as product manager for a hose, but a lot of engineering goes into designing the right braid. A metal core hose that you see on the left is extremely strong in hoop strength because of the convolutions. You can almost stand on the core and it won't collapse. So what the braid needs to do is withstand pressurization and making the hose elongate under pressure. A metal hose wants to grow in length, not in diameter when it's pressurized. So the braid is intending to support the hose from growing in length. This makes the braid much shallower, about 42 to 45 degrees. And a lot of engineering goes into determining what the right braid is, what the right braid angle is for that hose. On a PTFE or thermoplastic softer core material, the hose wants to grow in length and it wants to grow in diameter. Because of this, the braid needs to support the hose in both directions, and it changes the braid angle, makes it a different angle depending on the hose design and hose size, but it tends to be more 53 to 55 degrees. And these again are very important things to understand when selecting the right hose. And then of course, braid material is going to impact temperature rating of the hose. It's going to impact price of the hose. And then what we also have is what we call a braid package, which is the wire size and count. There's different wires to use when braiding. Of course, the fewer wires, the less expensive the hose will be, but they need to be thicker wires, and therefore that will be a much more rigid and less flexible hose. The more wires, the thinner the wires can be to achieve the same pressure rating, but the price will go up. So it's all what is the application looking for? Is it a dynamic application where the hose needs to be more flexible, or is it more of a static application where the hose can use bigger, thicker wires to lower the cost? And all this needs to go into part of that selection, selecting the right hose for the application. Some quick examples of this. Again, there's a lot of expertise that goes into selecting the right hose. And because of this, Swagelok has established a group of what we call hose advisors. They're highly trained sales and service center associates that are able to go out and help select the right hose. So if this seems like a lot of information, don't worry, we have people that can help you out. Some examples are, this is a tire press, and the particular hose you see in the picture that's U-shaped goes through about a 6-foot vertical motion, and what that was doing was damaging the hose, and it was failing in about a month. We were able to go in and select a hose with the better braid package, better suited for this steam media that was 200 degrees Celsius, 400 degrees Fahrenheit about. And we now have this hose in service for over 30 months. I need to update my slide. And it has not failed. So just one example of, taking out a perfectly good rubber hose, just put in the wrong application. And we put in a hose that's a little more expensive, but it's now lasted over 3 years. So of course it's a better solution for that application. I spoke at the beginning about how hoses are a wear item. And again, I can't stress that enough, but just planning for the right maintenance schedule will lead to incredible savings. Hoses are a soft material and they will wear out just like the tires, right? And so planning for the right maintenance program, right maintenance schedule will make the downtime less expensive, make the downtime at a more convenient time for the operation. And we've seen users of our hoses save hundreds of thousands of dollars annually because they can plan for the right rebuild schedule of their system. And then something else that we like to stress is hoses are a very commonly handled component. We don't go around and handle tubing very much because it's rigid, and we don't handle fittings because they're rigid, they're stuck. But hoses are very commonly disconnected, connected, dragged around. And for that reason, we need to make sure that we plan for associates to handle hoses. Braid wires can become sharp if they're damaged, and so that needs to be considered. But also, the outside of a hose can become extremely hot or very cold, for that matter, in a chiller application. But this picture here on the left is what we call a steam tattoo, where this individual rubbed up against a 200 degrees Celsius steam line and left a burn mark, and that's what you see here. And for this reason, hoses have a lot of different accessories readily available, things like insulation so that handles so that the outside of the hose is safe to handle, different guards to protect users from braid wires, or protecting the hose from rubbing against a corner or whatever it might be. And so those things need to be considered when looking at how often a hose is going to be handled. So at this point, are there any questions before I move into our next topic?
I don't believe so. Nope.
Okay. So the next part of today is we're going to talk about hose routing and how to prevent kinking. I think we all know what a kink is in a hose. We all have garden hoses, I'm sure. And, we all go around and kink the hose to get your little brother to look in the end of it and then let the hose go and he gets all wet. And that's fine with a garden hose, but in a general industrial hose, it's actually very dangerous thing to do. Here's some examples of hoses that have obviously been permanently damaged. And the concern with doing this, unlike a garden hose, is that there could be something dangerous inside of these hoses, and the hose has been permanently damaged to the point where it no longer is going to maintain the same pressure. And we've proven this in our labs where we kink a hose and burst it, and it does not maintain the same burst rating. So it can become a safety concern. Just to make sure we're all on the same page, what kinking means is that you've bent it beyond the point of elastic deformation. So it's now plastically deformed, and as the hose bends, as you see in the picture, it becomes oval, and that stretches the material more and more to the point where the sides of the hose are permanently damaged. And this can be a concern because as you know, with the garden hose, we can straighten the hose back out and kind of massage it back into a circle, and it looks fine. It looks like it has never been damaged, but that plastic deformation has still happened. It might look fine, but it does not maintain the same pressure, and it can become something where the hose looks okay, but it could, if pressurized to a certain level, depending on how much damage was done, it will burst prematurely. So again, it's a very dangerous thing to do, and people don't normally think of it as a big deal, but it really is. A very common place a hose kinks is right at the end connection for reasons like you see here in this picture. And so we always say, allow for a certain straight length at the end connection before a bend starts with the hose. And then the maximum bend or minimum bend radius, the most you can bend a hose, is always listed for every hose supplier. And we call that the minimum bend radius. And there's two different minimum bend radii. One is a static for a hose that's not doing any moving, and one is a dynamic for a hose that's going through motion on a regular basis. And these are all listed. This is just a snapshot out of the Swagelok catalog. As you see, for whatever hose series this was, I took a picture from, we have a static bend radius and we have a dynamic bend radius for each size. And it's important to understand that what we're saying is, if you bend the hose beyond that radius, smaller than that radius, I should say, the hose will be permanently damaged and no longer maintain the same pressure rating that we list in our catalog. So if you maintain radii larger than what's listed in this, you will not damage the hose. So the way I didn't realize I had a build on this slide. The way we determine, so how do we determine minimum bend radius? And there are various ways to do this. On a metal core hose, which if you think back to the picture I showed at the beginning, it has a convoluted core. As you bend the hose more and more on the inner radius of that convolution, the convolution peaks will become closer and closer. When those peaks touch, we call that the minimum bend radius. We don't want those peaks to push into each other as you bend it further and further. So that's pretty straightforward on a metal core hose. That's how we determine that one. On a soft core hose, like a Teflon core, what happens is this ovalness that you see in the picture, and we continue to bend the hose with a marble that's 80% of the original diameter. And if the marble rolls through the hose, it hasn't been overbent. Once that marble, that's 80% of the diameter, gets stuck because the hose has been bent too much and went too oval, then that's the minimum bend radius. That is our method of doing it. There is no industry standard. So when we go and determine these bend radii, we take a fairly conservative approach. We want to make sure that the hose was not damaged. And we feel that this 80% marble rule is a nice, safe approach. Everyone could do it differently. So it's always important to understand how minimum bend radii are determined. With dynamic hoses, it's a little different. There is an industry standard. And the way that is done is in the picture you see on the right. The hose moves up and down a certain distance as called out in the standard, and it's under full pressure, and it needs to pass 10,000 dynamic cycles. If it passes 10,000, we can reduce the radius, and retest. And as soon as it doesn't pass 10,000 cycles, we know we passed the minimum bend radius dynamically. So again, we want to make sure that we look at hose routing. This is a very common poor routing technique that we even have sometimes on our shop floor. I go around and try to get them fixed, but it's very easy to connect a hose out of a horizontal end connection and allow the entire weight of the hose to pull down on that end connection. That will damage a hose much faster than you think, because 24 hours a day, 7 days a week, that entire weight of the hose is pulling down on that end connection. And then if there's liquid, of course, flowing through this hose, that additional weight will be pulling down on that end connection. This is done most often because people are trying to save money on buying an elbow, but the hose itself will will be damaged and need replaced far sooner, be more costly than the price of that elbow. So again, look for these types of things. These are simple fixes, and the hoses will last far longer. With dynamic applications, there's a list of equations, and again, my intention isn't to teach us all these equations today, but please understand that these equations exist. Swagelok field engineers and hose advisors are well versed in understanding them, but they're there to help determine the right length of hoses in dynamic applications. There's been many times, like that tire press picture I showed, where a hose is put into an installation and it looks like a good length, but as the hose goes through its motion, it doesn't have enough length to go through the full motion. This will break the hose instantly, practically. So it's important to understand how long a hose needs to be to see a full range of motion without violating its dynamic minimum bend radius. And again, these are things that we can always help with if needed. And then lastly, the death of a hose, a fast death to any hose is twisting it. The core tube material, whether it's metal or Teflon, doesn't withstand twisting really at all. And the most common twist that we see in any hose application is what we call bending in two planes. What this means is you see the picture on the right that we say is incorrect. That hose is coming out vertically out of a plate and twisting around and moving into a horizontal port that's moving back and forth. If you picture the way this hose is bent, if I disconnect this hose but maintain it in the same shape, it won't lie down flat on a table. It's bent in two planes. That's putting severe twist on that bulk hose, on the core tube, and it will fail very, very quickly at the end connections. A simple rerouting, like you see on the left, where we have a static hose, it could be tubing as well, of course, brings that port up to the same plane. And now as that connection moves back and forth, it's only moving on one plane. I can take that dynamic hose, disconnect it, keep it in that same shape, and it'll lie down flat on a table. This hose will last hundreds of times longer than a hose that is being bent in two planes. Okay, so that takes us to the end of section 1. Again, we have a section 2 planned. We do have a lot of additional training material on hoses because, again, we understand that there is a lot that goes into this. It's not just every hose is a hose. We have a class called Hose Essentials that we offer through your sales and service center. We do have hose advisors, like I said. They can come out and do any kind of service that is needed around hose recommendations. We have a group of global field engineers that are also well trained on all of this. And like I said, we have part 2 coming up in the very near future. And to that point, part 2 is scheduled Thursday, November 13th at 11 o'clock, I believe, Pacific time. And what we're going to go through during that, again, is a lot more advanced topics, I would say: static dissipation versus conductivity, how to determine permeation in hoses, and how to maximize metal hoses for dynamic applications. And with that, Jen, I think I'd like to turn it over to any questions you might have received.
Yes, thank you, Doug. So we will stay on for a few minutes here, and if you're able to ask any questions you have or want to listen in, please feel free to stay on with us. The first question is around the hose size ranges. So I think that is probably pertaining to Swagelok and what types of size ranges are offered.
Yeah, so we offer hoses in size diameters from 1/8 inch to 2 inch. We actually have the opportunity to, that's as standard in our catalog. We do go up to 4 inches though, that aren't listed in our catalog. So depending on the hose series, we do have the ability to go up to 4 inch in diameter, but 2 inches is our standard maximum.
Great, thank you. I actually missed one before that, and that is, how should hoses be properly bonded and grounded? Good question.
So that might be something we get into in part 2 when we start talking about conductivity versus static dissipation. It depends on the application, I guess is the short answer. It depends on whether or not the hose needs to be a grounding item or not. And we've seen applications where the customers want it to be conductive and grounded, or we've seen applications where they don't want it to be. So it kind of depends. Maybe not the best answer. And that might be one we take offline for a particular application.
Yeah, so if you want to follow up with your sales and service center, get with Doug as needed, or your field engineers and hose experts and answer that more directly. Let's see, we've got why are convoluted metal core hoses considered less clean than smooth core PTFE?
Yeah, they can be cleaned to the same level. What happens with a convoluted metal core, of course, the convolutions can trap material, and therefore it's not as drainable, maybe is a better word to use than cleanable or clean. They can be just as clean, if not cleaner, than a PTFE core hose, but they're not nearly as drainable, and I hope that makes sense.
Okay. We have a question around connectors and fittings. Doug, do you have a recommendation on resources for learning more about hose connections and fittings?
You mean what end connections are available, I assume?
Yeah.
Yeah, we can maybe handle that one offline as well. We have a software tool that lists all the end connections that we've done in basically recent history at Swagelok for hoses. We'd be happy to share that. We list quite a few of them in the catalog, but actually our list of possible ends go well beyond that.
Okay. I'll follow up with sales and service center on that. In the example earlier of the tire press with repeated hose failure, the unexpected shutdowns must have been costly. What should operators do if they're worried about that at their plant?
Yeah, absolutely. So that's a big complaint we get with rapid hose failure, I guess you could say. What that particular customer was doing was stocking the hose, extra hoses, because they were failing so quickly. That, of course, is costly, but it allows them to get their tire press up and running much faster. We thought that it wasn't really acceptable for the hoses to be failing that fast, so we wanted to go in and work with that user on selecting a better hose. That allows them, of course, to then cut down on their inventory and save money that way as well.
Are PTFE hoses appropriate for vacuum applications?
Yes, they are. However, not to the same vacuum level. We say that a PTFE core hose is rated to 28.5 inches of mercury, if you use those units, but it's about a 95% vacuum. A metal core hose is rated to 99.9999% vacuum. About 0.001 millitorr, I believe, is what it was. So they're different vacuum ratings, and it's important to keep that in mind when selecting a hose for vacuum.
Okay. Are the ratings provided for smooth core PTFE hoses with respect to permeability, such as leak rate through the hose versus pressure?
Yeah, good question. We do not publish those. We have a lot of data, and we'd be happy to do test reports. Again, we'll get into permeation a lot more in part 2, but we understand that we see an enormous range in performance just within PTFE, and it depends on how the actual core tube was made. You can have about 40 times difference from one manufacturing method to another. And so it is important to understand how the hose is made when selecting a PTFE hose for gas applications.
Good. And last question that I have in email is, what do you do when two hose selection parameters are at odds with each other?
Yeah, so you have one of those, for my cheat sheet, you have a green dot and a red dot. A lot of times what we tend to do is the PTFE core hose tends to be a general middle ground that works well in all applications. So many times we start with that. But other than that, our hose advisors know how to look at a application and determine if we want the metal core hose is going to perform well with this, but not with this parameter. But that parameter is a smaller factor in the overall application.
That seems to wrap it up today. For anyone that didn't get their questions answered, please reach out to your Sales and Service Center representative, or my email is in the chat if you need help identifying who the proper person to reach out to is. I can help set that up. And we will work with Doug on the more complex questions, and really appreciate everyone's time today. And I hope you can join us again on November 13th for the second phase of this presentation. Have a wonderful day, everyone.
Yeah, thank you, everyone.